Hi everyone, Mr. Zhang here. Today we are going to talk about two ideas in nuclear physics. One of them, well, maybe they're really the same, but they're called mass defect and binding energy. Okay, so what is it? Okay, it's basically this idea that if you have these four hydrogen and you add their masses, right? So if you add their masses together, it's going to be greater than the mass of helium. Right? So if you look at the mass number of helium, it is 4. And if you look at the mass here, it should be like 4 as well. But you can see that here, right, on the scale, it is greater than this. Now, if it's kind of saying, like, if you fuse, right, it's kind of saying if you do a fusion of these 4 hydrogen atoms and you get helium, there's a missing mass, right? There is a mass that somehow disappeared, and this mass that we're combined into helium is less than this over here. Okay, so that is what the mass defect is. It is, right? So to put it into words, we'll say that it is the difference between mass of the nucleus, and its individual parts. Okay, so it's the idea that if you take the individual parts here and you separate them out and then you count them and you look at the mass, it will be greater than if this whole thing is together, which is a little weird, right? So it begs the question, well, mass can't just disappear. Where did this mass go? Okay, the simple answer to this missing mass is that it went to become energy. It became energy via this equation, mc squared. Right, so if you find this missing mass, which is delta M, you can actually figure out where or how much of it was turned into energy. Okay, so that's the idea here. Now let's introduce a similar concept called the binding energy. So I'm going to look at the slides that we are using in class. Let me check here. Okay, so it's essentially this idea that if you want to go the opposite way, right? Let's say you want to go from here, right? So now maybe I should do it in pink. Let's say that you want to go from here and you want to separate them into here. The amount of energy that is required, to go from full like this to individual parts like this is called the binding energy. Okay, so the written up definition is is that the binding energy is the amount of energy required to separate a nucleus into its individual parts. Okay, so that's the idea here. So you can think of it like the amount of energy required to hold all of nucleons in place in the nucleus. Okay, so it's the amount of energy that will keep all of this together. Right, so that's the idea. So what you have to remember what you have to remember about protons and neutrons, right, are forces. there's two forces, right? So there's the strong force and the electric force. So remember that protons. Whoops. Remember that protons repel, right? Protons, right? So they repel each other, and I don't know if this is right. And okay, I'm pretty sure this is right. And it comes from the strong force. The strong force is an attractive force. Call this an attractive force between protons and neutrons. Okay, so where does the binding energy come from, or why is the binding energy required? Well, it's because of mainly the strong force, but a little bit of this as well, right? So well, really the electric force helps with that, but it's really the strong force, right? So if you look at it from like an equation point of view, you have a nucleus which has a smaller mass, and you want to get a greater amount of mass, right? So if you want to get a greater amount of mass, you have to add in energy, which, right, is the same thing as mass via this equation. Okay, so that's what the binding energy is. Okay, so if you want to separate them, this energy that you need, that's called the binding energy. Okay, so let's keep on. Okay, so what about binding energy per nucleon? It is basically the energy required to separate the nucleus divided by number of nucleons. Okay, so it's this idea that if you have delta M, right, the mass defect, and you multiply by mc squared, you get E. You take this E and you divide it by a number of nucleons. That would be the energy per nucleon. Okay, so that's what the binding energy per nucleon is. Okay, it's getting pretty late here, so I'm gonna finish this part, and I think I'm gonna let you guys try to figure out the rest of it on your own. Okay, so measure of how stable the nucleus is. There are two things that we care about when it comes to stability. First off is how much energy on average does each nucleon give up to be part of its whole, which is kind of like the same idea as this next one, right? So the more binding energy per nucleon in an atom, the more stable the atom is. Okay, so on average, if you look at the average and you can see how much energy each nucleon is willing to give up to be a part of the whole, then you can know how stable it actually is. And when it comes to stability, there's actually lots of different kinds of graphs that you can look at to get an understanding of how it works. I don't know why I'm drawing on here, but essentially, okay, so let's look at this graph here. On the y-axis is binding energy per nucleon, and here is the mass number. So as you can see, there seems to be some kind of, please don't mess with me. Why is this thing messing with me? Okay, so you can see that it starts low. It starts pretty small, like here, and then it jumps. Like it really jumps like this. Okay. All right. So this is pretty interesting. Here are two things that you need to know. If you're going this way, this is going to be fusion, right? So if you want to go up this way, it's going to be fusion. And if you're here, you're gonna, and you want to go this way, this is fission. So the most stable element according to IB is going to be iron 56. As you can see, iron sits right here where it is super stable. Okay. Alright, once you get to this point, then you start going this way. Which elements do not like, I suppose you can say. Okay, so it says on the graph identify the portion that undergoes fission and fusion, and which, okay, so we already did that. Next part. So this here, I think I'm just gonna let you guys do this by yourself, but you need this information here, and you want to calculate everything in U's, okay? So maybe I'll do this first part here, actually. The atomic nucleus C14 has this, okay? What is the total mass of the constituent protons plus neutrons? So here we know that carbon 14 has 6 protons, okay, because of the atomic number. Right, so we have 6 protons. So I want to find M total. 6, 1.007 U, right, plus 8, 1.009 U. So if you add this together, you should get, I did it on paper here, so let me check. You should get about, oh shoot, sorry, I went too far. So you should get about 14.114 U. Okay, that's what you should get. And then if you subtract it, so it's to compare your answer from the mass of the nucleus. So it wants to compare this answer to this answer, right? So it's going to be 14.114 U minus 14.003 U, and that's going to give us about 0.114. No, sorry, 1 U. So this is a mass defect, right? So that's what we're calculating. And if you take the mass defect, right, which is delta M, and you multiply it by C squared, well, you have to convert it first into energy. Then you can find the binding energy, okay, that was required for the mass defect to be there. Okay, this calculation is the same as the one above, same as that one. Here's an interesting question. Why would hydrogen have no mass defect? Well, because hydrogen, we can say hydrogen has one proton. One proton. Also, there is no mass. There is no difference between its whole and the constituent because it's the same constituent parts, because it's the same, right? There's only one proton, that's it, right? It's like this. So how can you have a mass defect? You can't. Okay, so I'm gonna let you guys read the rest of this, and I think you can figure out the rest of it on your own. Okay, thanks. Bye.